Our last topic of discussion, enols and enolates. These are more carbonyl reactions, but they're a totally different type. Let's see what I mean. First of all, let's make sure we're clear on the definition, what we mean when we say enol. This compound on the right is an enol, the specific kind of enol that we will discuss all throughout this chapter. It's an alkene and an alcohol on the very same carbon. That's very important. The alkene and alcohol has to be on the same carbon. So enols and ketones are in equilibrium with each other. In general, equilibrium favors the carbonyl version, and there's only small amounts of enol present in solution for almost all carbonyl compounds. But for some carbonyl compounds, the enol version is actually favorable. Have you ever really thought of regular phenol as an actual enol compound? Probably not. But phenol is much more stable as the enol than it is as the carbonyl, because as an enol, it's an aromatic compound, and aromaticity, as we discussed many weeks back, is a very stable thing. This compound on the right is actually more favorable as an enol as well, because of a couple of things. For one, it's a conjugated compound over here on the right when it's an enol, and conjugation provides stability. Just like aromaticity provides stability, conjugation is another way to provide stability. Aromatic things are more stable because they're more conjugated. Remember? In addition, in this molecule, you can have a little hydrogen bond between the oxygen of your remaining ketone and your H of your OH enol thing. That little six-membered ring that's formed from a hydrogen bond provides a little extra stability. These compounds, this compound is called a beta diketone. That's because the alpha carbon, which is the carbon next door to the carbonyl, remember, common nomenclature of carbonyl compounds. The alpha carbon is the one in the middle. There's a ketone right next door, so that's a beta diketone. Two ketones, they are beta to each other. Beta diketo compounds commonly exist as one carbonyl, one enol in solution. So that's enols. What the heck is enolate? Well, in base, you can deprotonate the H of your enol to make an enolate. So if you lose the H off of your enol, you get this compound on the right, which is an enolate. This is sometimes referred to as the oxyanion version of the enolate. That enolate has resonance. All enolates have resonance. And I just noticed as I said that this arrow says equilibrium. This is not equilibrium. This is 100% resonance. So you can resonate that negative charge to exist on the carbon. And so this version on the left is called the carbanion version of an enolate. So the bottom two compounds are enolates. They are resonances of each other. These compounds are not resonances. These compounds are tautomers. Remember, that's how you change from a ketone to an enol or vice versa. These compounds are tautomers. These compounds are tautomers. Resonance, tautomers, tautomers, tautomers. Got it? Good. So we're going to use these enols and enolates as nucleophiles in these coming reactions. We're going to classify these reaction types as alpha carbon reactions. Why? Because in this carbanion version, it's the alpha carbon that has a negative charge. It's the alpha carbon that's going to act as a nucleophile to attack things. In acidic solution, enols are going to attack things, but what position is going to attack? The alpha carbon. So if you drew a resonance thing of this enol up here, you could see why that alpha carbon, that's an H over there that you can't see. You could draw a resonance version where the alpha carbon has a negative charge. That alpha carbon can attack things, whether it's an enol or enolate. The alpha carbon is the nucleophile in all of this chapter. So here's a carbonyl compound. It's an ester. It has an alpha hydrogen. Here's a ketone. It has an alpha hydrogen. Here's another ketone ester combo thing. It has an alpha hydrogen. Let's draw these reactions on paper. So given these three carbonyl compounds, if we react them in some sort of base, we're going to discuss very painful detail what that base is, but that base can pluck an alpha hydrogen. Why would you want to pluck an alpha hydrogen? Because an alpha hydrogen is more acidic than a standard alkane hydrogen. See, this is an sp3 carbon. That's a standard alkane carbon. But we can pluck an alpha hydrogen. We'll explain why that's an okay thing to do momentarily. Base can pluck an alpha hydrogen to give me the same kind of thing. Base can pluck an alpha hydrogen to give me the same sort of thing. So all three of these products I have created are enolates. Why are alpha hydrogens more acidic than standard alkane hydrogens? Well, like the answer to so many other organic questions, resonance. That negative charge can be delocalized to that oxygen. So this blue structure is the oxyanion version of that enolate. Still an enolate, just the oxyanion version. Same. Uh-oh, what's different down here? There are two places that negative could be distributed. So if we do a way back throwback, which of these three acids are strongest? The strongest acid has the most stable conjugate base, and the most stable conjugate base has the more resonance pictures. So this bottom acid is stronger than these previous two acids. On the slides, it actually gave you pKa's, where you could see this top one has a pKa of about 25. This middle one has a pKa of about 20. And this bottom one has a pKa of 10.7. So first thing to remember is alpha hydrogens are more acidic than regular alkane hydrogens, as in it's much easier to pluck a hydrogen here than any of these hydrogens or these hydrogens. The alpha hydrogen is much more acidic because of resonance of the conjugate base. But these alpha hydrogens of these three acids all have different pKa's, different acidity, based on the stability of the conjugate base. Apparently, this conjugate base is most stable, this is next, and that's last. If you go back to our reactivity chart that we've talked about so many times, remember ketones are more reactive than esters. The real reason for that is because esters have a donor group over here. Donors make acids weaker. Donors make bases stronger. They make acids weaker. Oh my Lanta, we come full circle. Isn't it great? So we need to be able to rank acidity based on just recognizing patterns and looking at functional groups. But additionally, we need to be able to figure out what base is capable of deprotonating these things. So that's where the slide has more information to tell you that water has a pKa of 15.7. Ethanol has a pKa of 16. And this guy, whoever this guy is, has a pKa of 36. So if you remember, if you have an acid plus base, that's going to yield a conjugate acid and a conjugate base. Remember, equilibrium always favors the weaker acid-base pair. So you're going to favor the larger pKa. So what does that mean? That means if we took that top ester and we added hydroxide to it, we could draw this as a potential product, just like we've done above, where we're substituting in hydroxide for the base that's actually doing this deprotonation. The acid on this side has a pKa of 25. The acid on this side has a pKa of 15.7. So equilibrium favors reactants. Does it mean you have zero product? No, you're going to have a little bit of product, but not a lot. But if I want to use hydroxide to try and deprotonate that beta diketo compound, well, let's look at the pKa of this. There's my enolate. Acid on this side, 15.7. It's water, it's the same. Acid on this side, 10.7. Equilibrium favors the products. So if I compare these two reactions, in this top one, equilibrium favors reactant. In the bottom one, equilibrium favors product. But remember, equilibrium is defined as the point when the rate of the forward reaction is equal to the rate of the reverse reaction. By definition, equilibrium means you have to have some of the reactants present and some of the products present. But this one will have mostly reactants, a little bit of product. This one will have mostly product with a little bit of reactant. So these two examples are using hydroxide as the base. We were also given the pKa of ethanol. So that means we could use ethoxide as the base. Ethanol is pKa 16, so it's practically the same as hydroxide here, as in the top reaction would favor reactants, the bottom reaction would favor products. But that other acid, this nitrogen acid thing, has a pKa of 36. So what that means is if you use this base, well, let's stick this up here. If you use this base, all of a sudden, equilibrium favors the product, because this is pKa 36 compared to 25. So this thing favors formation of the product. This thing often comes along with lithium as the counter ion, and his name is lithium diisopropyl amide. He gets an acronym because he's so famous, LDA, lithium diisopropyl amide. So let's give you a take-home message before we move along. When I use a base like hydroxide or ethoxide, depending on what exact thing I'm trying to pluck an alpha hydrogen from, hydroxide may favor reactants, hydroxide may favor products. Ethoxide may favor reactants, ethoxide may favor products. But LDA is super strong. It's a beast. So when I put LDA with any of these carbonyl compounds where I want to pluck an alpha hydrogen, LDA will favor product formation. We will actually say that when you use a weak base like hydroxide or ethoxide, the process is reversible. When you use LDA, we're going to say that that favors products and products only. We're going to say that LDA is so strong that it exclusively favors products with no reactants left. This reaction with hydroxide, reversible. This reaction with LDA, irreversible. We would say that LDA quantitatively deprotonates your alpha hydrogens, meaning you have no leftover carbonyl version, you have all enolate version in solution. That may be confusing so far, but hopefully it will get more clear as we work through more things. So we spent a long time talking about that because it's unfortunately a big deal that you get this. I never actually said in all that time we were talking about this, we plucked the middle hydrogen off of this bottom compound, but aren't hydrogens over there also considered alpha? They are, but the middle alpha is much more acidic than the left alpha because of resonance. Hopefully you saw that without me explicitly saying that. So here's a table that I stole from your textbook. This says that a normal alkane has a pKa of about 60, and yet all of these things have a pKa of 30 or less. The alpha hydrogen next door to an amide, pKa 30. That's the least acidic of everything on this table because remember, amides were way down there on our reactivity chart. Amides, esters, ketones, aldehydes. Ooh, it kind of sounds like it's going in the order of our chart, but in reverse, right? Yeah. One little outlier is this nitrile. Beware of that. A nitrile is a very strong electron withdrawing group, so it makes that alpha hydrogen more acidic. Remember, electron withdrawing groups make acids stronger. Electron withdrawing groups make acids stronger. So here's a whole bunch of other things you can see. These hydrogens that are all highlighted in yellow are considered alpha hydrogens. It's explicitly an alpha hydrogen when it's next door to a carbonyl, but this hydrogen down here between two nitros is really very acidic. We're going to still call it an alpha hydrogen, even though it's not next door to a carbonyl. So our first type of reaction we will do with these is alpha halogenation. Put a halogen on the alpha carbon. A few details about it before we draw things on paper. In acid, you replace one alpha hydrogen. In base, you replace all alpha hydrogens. There's something special that happens if you have a methyl ketone in base. And then we're going to talk about the hell of a hard Zielinski reaction, which is when you react with a carboxylic acid instead of a ketone. Let's do this. So let's do an example that's a methyl ketone. What that means is one side of your ketone is a methyl. Let's do it in acid. So tosic acid and Br2. In acid, it's an enol that will act as your nucleophile. So in acid, the very first thing to do is tautomerize. The official mechanism for a tautomerization goes like this, but we may not always draw this in painful detail. Protonate the carbonyl oxygen. Some base takes an alpha hydrogen to give you an enol like that. We will shortcut that tautomerization mechanism some, but I may not force you to draw the tautomerization mechanism all the time. So because we're in acid, it's an enol that's doing the nucleophilic stuff. So then once you have your enol, attack the thing that's ready to be attacked. And because this is alpha halogenation, we're going to attack the BR. I folded down electrons at the same time as attack so that I could get to this version. But if you did not fold down electrons at the same time, you would get a structure that looks like this. What's the relationship between these two compounds? They're resonance structures. That's all. So which resonance is more favorable? Left one, right one. Left guy, right guy. The one on the right, because everybody has an octet. Hopefully you yelled that at your computer. And then some base cleans up. It may be bromide. It may be the solvent. Who knows? Some base cleans up. And we get here. Ta-da! Alpha halogenation. Remember the notes said in acid, one alpha hydrogen is replaced. We didn't have any alpha hydrogens on this side. That's how I knew I needed to replace over here. But only one gets replaced in acid. In base, the story's a little different. So let's draw this one in base. In base, the first thing we're going to do in so many of these reactions is pluck an alpha hydrogen. Make an enolate. Does equilibrium favor enolate formation here? Not likely, because this is a ketone and hydroxide. But do you have a small amount of enolate present? So you can draw the resonance of this enolate if you want to, but I like to keep it in the carbanion version because it's then the carbanion version that attacks the thing that's ready to be added. Well, that's cool. That's the same product I just made. But what's different this time is you still have alpha hydrogens and you're reacting in base. If you compare this purple alpha hydrogen to this blue alpha hydrogen, the purple alpha hydrogen is much more acidic. Maybe I overemphasized that. The purple alpha hydrogen is more acidic because this is the alpha hydrogen of a ketone. So you've got one electron withdrawing group next door. This is still the alpha hydrogen of a ketone. So you've got one withdrawing group ketone next door. But adding the bromine creates more inductive pull on this hydrogen, making this hydrogen more acidic. So you made a little bit of enolate. That enolate added a halogen. This hydrogen more acidic than it was before. So you make a second enolate. This one. That enolate attacks the BR thing, whatever you're trying to add. This is alpha halogenation, remember? So we attack the halogen. And guess what? This hydrogen that remains even more acidic than that one was. So hydroxide is going to take it again, pluck an alpha hydrogen to make another enolate, a third enolate. And then attack BR. So we really should specify that you need excess hydroxide and excess halogen, because in base, you're going to replace all alpha hydrogens. We chose this specific example because it was a methyl ketone. And there was another note on our notes that said a methyl ketone does something special. If this were a different type of ketone, in base, you still replace all alpha hydrogens, but this next bit is specific to a methyl ketone. So because this is a methyl ketone, I'm changing colors. For orange is specific to methyl ketone reaction. Hopefully you pick up on that. Because you've replaced all of the hydrogens on this carbon with halogens, this 3 halogen thing is a decent leaving group. So we attack the carbonyl carbon this time, because this whole thing is now considered a decent leaving group. Only after you replaced all alpha hydrogens with halogens do you attack the carbonyl carbon. And then you fold down and kick out the weakest base, the best leaving group. So that carbon with 3 halogens on it is now my best leaving group. And I kick out a carbon with a minus, but 3 halogens connected. And one final acid base, deprotonate, you get a carboxylate and HCBr3. This compound is named bromoform. Ever heard of bromoform? Maybe not. I bet you have heard of chloroform. Where have you heard of it? Iodoform is the iodine version. So this reaction of a methyl ketone plus excess base and halogen is called the halo form, because one of your side products is a halo form, a chloroform, bromoform, iodoform. Remember, the orange part is exclusive to methyl ketones. Methyl ketones are what make this halo form. A common qual test for methyl ketones are using iodine, because iodoform is a yellow precipitate. So if you get a positive iodoform test, it tells you that you had a methyl ketone in your unknown thing. Got it? That's alpha halogenation. So we did the mechanism for in acid and in base, and we made it specific a methyl ketone. Carboxylic acids can also do this. It's called the Helvehard-Zielinski. Helvehard-Zielinski. We'll see that one next, but we're not responsible for its mechanism. So the Helvehard-Zielinski, HVZ. First, you add PBr and Br2. That's old news. What the heck does that do? It turns your carboxylic acid into an acid bromide. But wait, something else just popped up. That acid bromide can also be drawn as the enol tautomer. Is the enol tautomer favored at equilibrium? Nah, but is there a small amount that exists? Yeah. So because this reaction is not ran in base, it's the enol tautomer that acts as the nucleophile. That nucleophile then attacks Br2 to end up with an alpha bromide like that. And then finally, water in the end does hydrolysis, but hydrolysis on your acid bromide, not your alpha bromine. So there's our final product. Mechanistically, could we draw it? Yeah, potentially, kind of, sort of. Do we need to be able to? Nah. The overall result is carboxylic acid plus PBr and Br2, followed by water, because water has to be added to hydrolyze the acid bromide, results in an alpha bromo being added to your carboxylic acid. Let's see it in action one more time. PBr and Br2 followed by water, alpha bromo on your carboxylic acid. And then you can do various things with that alpha bromo. Remember, alkyl halides are some of the most flexible functional groups we've seen. So if I add KOH and ethanol and heat, that's a secondary alkyl halide. Secondary alkyl halide anions? Yes. Strong base? Yes. And I'm even heating it to indicate that I want to do elimination, E2. So I get elimination. Alkene is formed. But what? Why is it a carboxylate, not a carboxylic acid? Well, because it's all in hydroxide. That's a base. Deprotonate that carboxylic acid for sure. Okay, next. Alkyl halide, that's secondary. Anions? No. This one, meh, it would maybe do SN1. It would maybe do SN2, but it's definitely going to do substitution rather than elimination. There's our substitution. It's also a carboxylate because ammonia, nitrogen, amines are bases. Substitution product there. That's actually an amino acid product. Check it out. This bottom one, how is this bottom one different from this one over here? It's not heated, so it's trying to indicate that you want to do substitution going south instead of elimination. There's an alpha hydroxy acid. AHA, is, you ever heard of them in dietary stuff? Alpha hydroxy acids. Cosmetics. Check it out. And this last one over here, cyanide and water, substitution, SAN2. Cyanide's real good at SAN2. There's our alpha cyano acid. All of those are carboxylates because all of those are under basic conditions. We've been at this long enough. Let's call this one done.